In today's video, we're going to be looking at section 11.4, which looks at testing hypotheses, this time about a population proportion. If you remember back to 11.2, we were dealing with hypotheses and testing hypotheses that dealt with a population mean. So you always had a null hypothesis that said that the population mean equaled something, and then you had an alternative hypothesis that stated that the mean was actually different than, less than, or greater than what you thought that initial value was. Okay, this time we're dealing with proportions, so it's very much the same thing, but this time you're going to have the null and alternative hypotheses are going to be about a population proportion. So they're going to say, okay, I think that my population proportion is equal to a certain value, but my alternative hypothesis says that it's going to be not equal to, less than, or greater than that value. Okay, and it's all based on the fact that they thought that their population proportion equaled a certain thing, but they've got some sample data that had suggested something else, so now they need to test this. Okay, so it's very much the same as what we have done before. So you're always going to end up with these hypotheses. You're going to have your null hypothesis, which is going to say that your population proportion equals some value. We'll call it P0, okay? It'll be whatever value they think it is, and it's always as a decimal. So if they ever give it to you as a percentage, make sure you go back and put it as a decimal, okay? And then your alternative hypothesis is going to state that the population proportion is actually either not equal to, greater than, or less than what you initially thought it was. Okay, so it all depends on what the problem says, as always. So you could end up with a two-sided alternative or a one-sided alternative, whether that be left-tailed or right-tailed. Okay. So it's very much the same as what we've done before. We're just now dealing with proportions. A couple of things to be aware of. It's going to have the same step-by-step process as we had before. And again, I'm going to do it the long way and then show you the short way on the calculator. In order to do this, if you remember, when we did the population means and we were doing these hypotheses with population means, you had to make sure that either your population was normally distributed or you took a sample size that was greater than 30. That allowed you to take that test statistic, which was a Z transformation of sample means, because you had to make sure that your sample means were normally distributed. Okay, and in order for your sample means to be normally distributed, you either needed to have a population that was normally distributed, or you had to take a sample size that was large enough, and we always said it had to be greater than 30. So you had to have one of those two things in order to do this. Now when you do this, okay, something that you have to be aware of, and we did cover this when we did proportions at the start, okay, a few chapters back, you have to either have that your sample size times that population proportion value is greater than or equal to 10, and you have to have that the sample size times the proportion of people that don't have that characteristic, so it's 1 minus P0, okay, P0 is the proportion of people that have the characteristic, 1 minus P0 would be the proportion of people that don't have the characteristic. Multiply that by the sample size, and that also has to be greater than or equal to 10. What this basically ensures is that your sample size is large enough. So as we had before when we dealt with means, we either had to have a normally distributed population or you had to have a sample size that was at least 30. Now we have these two conditions when we deal with proportions instead of means, okay? You shouldn't have to worry about this too much. They don't tend to bring this up. It's just something to be aware of, okay? But what this allows you to do, okay, these two conditions, it allows you to say that the sample proportions are normally distributed. And that allows you to take that Z transformation where you deal with the sample proportions, because your sample proportions are now normally distributed, which therefore means you can get your test statistic, which is the Z transformation. So this means that your sample proportions are normally distributed. Which means that you can now take a test statistic which is the Z transformation of sample proportions. So the Z transformation, or that test statistic, is Z is equal to P hat is your sample proportion. So when they do this hypothesis test, okay, they will say, well, I think that my population proportion is this, but I have taken a sample and my sample proportion was instead this. Your sample proportion that you have is P hat minus that population proportion value divided by the square root of your population proportion times 1 minus your population proportion over n. Okay, we did this before when we did the Z transformation with these sample proportions. Then you're going to go through your 5-step process as we did before. Okay, it's going to be very much the same as what we have done before. This time you're just dealing with proportions. And again, I'm going to go the long way with this, but you can also do it the shorter way. Okay, so the first thing that you do, okay, step 1, is you're going to determine the null and alternative hypotheses. Okay. Whenever you do your null and alternative hypothesis, always remember that your null hypothesis always suggests equality. So it's always suggesting that your population proportion equals the thing that you initially thought it was. And then based on what they say in the question, we'll determine what the alternative hypothesis is. So is it not equal to what you initially thought it was? Is it greater than or less than? Okay. Then step 2, you're going to state the significance level. So you're going to state what alpha is. Okay. Alpha is that significance level. It's the level at which they want to conduct the test. It's the proportion or the percentage of time that they want to reject that null hypothesis. So if you've got an alpha, the significance level equal to 0.05, you want to reject your null hypothesis 5% of the time, and you want to fail to reject it 95% of the time in that case. Okay. Step 3 is to find that test statistic. So step 3, find the test statistic. Okay. And that is what we've just said. So that's that Z score, that Z value that we just talked about, which is the Z transformation. And it looks very much like the last one. It's just that your standard deviation over the sample size, that looks slightly different this time. But it's very much the same as what we've done before. Then step 4 would be to find the critical value. Okay, and that's based on this significance level alpha. And then you're going to compare your test statistic to that critical value. And if that test statistic falls in that danger zone, exactly the same as last time, then you know that you're going to reject the null hypothesis. But if that test statistic instead falls in the region where we're okay with it, that means that we're going to fail to reject. So find the critical value and compare the test statistic to the critical value. Okay, and then step 5 is just to determine whether or not to reject that null hypothesis. Okay, so it's exactly the same as last time, it's just that your test statistic looks slightly different. Okay, that's the only difference here. You should notice that in your homework, it's split into 11.4a and 11.4b. 11.4a, they're expecting you to go this long way with it. 11.4b is where they introduce that p-value again, where you can compare p to alpha and decide whether to reject or fail to reject that null hypothesis. So it's very, very, very much the same, okay? But I'm going to tell you that short way just so that you have it, and then we're going to do an example. Okay. The short way again is you're going to get that p-value, and that p-value determines the probability that you have a test statistic that is at least as extreme as the test statistic that you calculate. Okay, so if that probability is less than alpha, it means that your test statistic falls in the danger zone, which means that you therefore have to reject your null hypothesis. So if you get a p-value that is less than alpha, you're going to reject your null hypothesis. But if your p-value is greater than that significance level, you fail to reject. And it's exactly the same reasoning that we had when I drew it back in 11.2. Okay, so if you're unsure as to what I'm talking about with these p-values, go back and watch the 11.2 videos, 11.2b, A, B, and C, I think it was. But go back and watch those just so that you can see what I'm talking about with these p-values, because it is exactly the same theory. Okay. But there is one slight difference. When you do this p-test on your calculator, it is very slightly different. If you go to stat and then across to tests on your calculator, so you go to stat and then go to tests. When we have been doing this so far, we have been doing z-tests and t-tests. Okay, when we are dealing with means and hypotheses that deal with means, we either do a z-test or a t-test. We did a z-test when we were dealing with hypotheses that were dealing with means, and you knew what that population standard deviation was. So you knew that sigma value. When you didn't know your population standard deviation, but you knew your sample standard deviation, okay, which is more like a real world problem, you'd do a t-test. Now we are dealing with proportions. If you scroll down on that menu, you should see something that is called a one proportion z-test. In my calculator, it is option 5. Okay, so I've gone to stat, tests, and one proportion z-test. Okay, this is where you are going to put in the information from the problem, and it will then give you one of these p-values. Okay, so instead, when you do these problems to do with proportions, you are going to do a one proportion z-test. That is the only difference here. Okay. So your test statistic will look slightly different if you do it the long way. And if you do it the short way, you're just going to be using a one proportion z-test. Everything else is the same. Okay. I'm going to do a quick example here. If you want to follow along with this example in the notes, it is on the last page of 11.4, right at the top of the page, on that Google Drive document. So I'll read out this example and I'll write down the major points. So it says the mayor of a town has proposed a plan for the annexation of a new community. From a sample of 900 voters, so n is equal to 900, our sample size, in the town, 53% favoured annexation. So the sample proportion, with the sample of 900 voters, they said 53% favoured the annexation. So your sample proportion would be 0.53. Okay. A political analyst wants to test the claim that more than 49% favour the annexation. So this political analyst has come along and said that normally you would get 49% would favour the annexation, but he wants to test whether more than 49% favour the annexation, because he's looked at what's happened in this sample and thought that something else is different. So his population proportion of what he thought it should be was 0.49. Okay, so this 0.49, that's your P0 value. That's what he thought it would be. But now he wants to test the claim that it is in fact more than that. Okay, testing at the 0.01 level, so alpha is 0.01, is there enough evidence to support the analyst's claim? Okay. First thing, let's write out our null and alternative hypotheses so at least we know what we're testing. Okay, your null hypothesis is that the population proportion is equal to what they initially thought it would be, 0.49. Your alternative hypothesis is testing whether it is in fact greater than 0.49, because they've looked at this sample data and they've said, well, it's actually greater than, we want to test whether it is in fact greater than 0.49. Okay. Now, We know that alpha, if we went on to step 2, alpha is 0.01. So here what we have done, let's go back, we've done step 1, we've determined our null and alternative hypotheses, we've stated our significance level, okay? Then you could go ahead and find this test statistic, okay? I'm going to write this down, but you can go ahead and like figure it out on a calculator. So this test statistic, okay? The test statistic is Z is equal to, it's the sample proportion minus the population proportion divided by the square root of the population proportion multiplied by 1 minus the population proportion over that sample size. Okay, you can go ahead and quickly figure that out. I can do that on a calculator very quickly. Okay, I get my Z value is 2.40. Okay, so that is my test statistic. Now what I want to do is figure out my critical value. Okay, we have here a right-tailed test. It is one-tailed and it is right-tailed because we have a greater than. So it means that our tail is going to be off to the right, and we have a significance level here of 0.01. So if you draw this out, because we've got a right-tailed test with a greater than in there, okay, my critical value, I'm going to call it Z1, okay, is going to be my critical value. I know that the area under the curve to the right is that significance level because I know it's right-tailed with a 0.01 significance level. Okay, so I know that 1% of the time is where I want to reject my null hypothesis. So my rejection zone, that danger zone, is going to be off to the right. Okay, that whole 1%. If I had a two-tailed test, so if I had a does not equals instead of a greater than here, that was a does not equals, I would have to split that 0.01 between the two tails. If it was a less than, I would have all of that 1% in the one tail over here. Okay, but right now I've got a right tail test because I've got a greater than in my alternative hypothesis, and so I've got my whole 0.01 area under the right side, okay, of that curve, which means that here I have 0.99, okay, to give me a total of 1 under the area of the curve. I want to find my critical value. So to find the critical value, we are looking at a z-score, okay? Anything with proportions is always a z-score, okay? Don't deal with t-values here. We're always doing z-values. So to find a z-value, I always do inverse norm with my area under the curve to the left of the value with a mean of 0, standard deviation of 1 because I'm dealing with a z-value, okay? So when I go to, let me get this up on my calculator quickly. So I'm going to inverse norm, okay? My area is going to be 0.99. My mean is 0, standard deviation is 1 because I'm dealing with z-scores, which means that I'm dealing with the standard normal distribution. When I figure that out, I get 2.326 roughly, okay? So that is my critical value. Now what I want to see is where my test statistic lies. So my test statistic was 2.40. 2.40 is around here, okay? That is where my test statistic was. It is to the right of it, which means it falls in this danger zone. So what does that mean? It means that my test statistic is within that rejection region. It means that I need to reject my null hypothesis. So as the test statistic So we reject our null hypothesis in favor of the alternative hypothesis. Okay. So that means that given what we had with our sample data, given that the sample told us that in fact 53% of people favoured the annexation, that tells us that the prediction for that population proportion was in fact not correct, and we actually have to go with this alternative hypothesis. So in fact, it tells us that because of what we found in the sample, the population proportion is actually greater than the 49% that they thought it would be. Okay. So let's do this the short way. Okay, that's going the long way. But the short way, again, if we go to stat, go across to tests, one proportion z-test. Okay, P0 is the initial value that they thought that population proportion would be. So that's 0.49. Okay. The next line on the calculator says X. That is the number of things in the sample that have that certain characteristic. All you have right now is the proportion of things in the sample that have the characteristic, not the number. So whenever you do this, this is the one thing that is kind of off with this test compared to the others. It doesn't like decimals, so please don't put decimals in. I tend to, if I ever do get a decimal value for X, I tend to round up and it works for me. Okay, I always round up. So even if I get like a point, like let's say 30.2, I would always round up to 31. Okay, and it has worked for me. If you do run into any rounding issues with this and it makes you slightly off of the answer, please let me know and I will look into it for you and see if I can find another way. But for what I found so far, rounding up works. Okay, so in this example, what I would always do when you get to that X value, I would actually type it in and it tends to do it for you. So I would actually type in X would be the number of people with that characteristic, which would be 53% of the 900 in the sample. So if you actually type in under that X value, 0.53 multiplied by 900, it will actually give you that value of 477. You don't have to quit out and go to the main page and then come back in and type the value in. It tends to do it for you. So that would be X is 477, where I've just typed in 0.53 times 900 to give me the number of people in the sample that have that characteristic. N is the sample size is 900. Then the next line should be your alternative hypothesis. So you've got the proportion is actually greater than the initial value that you thought it was. And then you can calculate. Okay. That gives me a z value of 2.40. Okay. That was what my test statistic was. Okay. That's what this test statistic value was. P is that p value that I'm looking for. So we find that P is 0.0, it's actually got another 0 in there, 0.008, okay? And then they give you that sample proportion and they give you the value N for the sample size. This p-value is less than the significance level that we were looking at in the problem, which means again, we would reject that null hypothesis. So again, those p-values, typing this into the calculator under a one proportion z-test is way quicker than going through all this test statistic critical value stuff. Okay, and this thing will also figure out that test statistic for you in case a problem does look for it when you do your homework, so you don't even have to work that out. So be aware of that you can use that as kind of a shortcut. The only time you can't use it is when you've got to figure out what the critical value is. You may actually have to do that by hand, just as I did up here. Okay, you may have to go in and actually figure out that critical value, but the rest of it should actually be able to be done on a calculator. Just make sure when you use that one proportion z-test, please, please, please make sure that you get that X value correct. Okay, as I said, I've always rounded up if I get a decimal value, but if you do run into rounding issues, please let me know. But you have to put a whole number into that X value. Okay, you can't put a decimal value in, it won't like it. Okay, it won't run the program. Okay, so please have a look at that. The homework problems are very much like this and very much like what you did in 11.2, so it shouldn't be too difficult. But if you do run into problems, please let me know, especially to do with rounding, and I am more than happy to help and figure it out with you. Okay. If you've got any other questions, please let me know. If not, I will see you in the next video.